Hello. Hello. Okay. Welcome to the material science lecture today. 哎，你们就可以先离开了，我们就可以先离开了。好，这个没问题的。Right. Good morning, ladies and gentlemen. How are you? Good. So today, let's get started. We are going to go to the chapter 1, introduction. Right. You all know this is the course of material science, right? Okay. You all know this is English talk course, right? Okay, good. So chapter 1 is, I'm sure you're all familiar with this drink, Coca-Cola, right? In Chinese, we say 可乐, right? In Japanese, cola, right? Cola. Right. So when I was young, I used this. No, I don't have money to buy this, but I saw this in the television. There's a bottle of glass with Coca-Cola inside. Okay, this is the old type of the container for a drink, especially a sparkling drink. Sparkling is something with pressure inside. So when you open the drink, the carbon dioxide will come out, right? Because there are some the pressure inside the container is larger than the outside. So you need something to hold the pressure, and they use glass, okay, with a cap which is made of metal. And then when I was junior high school, there's an advertisement come out, which is something like this. It's a bottle, okay, and very light, lighter than this glass. Glass is heavy. When you want to fight, you can use this as a weapon, but you don't want, okay? But you cannot use this for fighting. You cannot, because this is light, soft. But how come this kind of container can hold the pressure inside? Because the technology improved. We found new material, and this kind of material is soft, light, and you can hold the pressure inside. So I remember there's an advertisement on television. I remember it very firmly. Is that this kind of bottle drop from for example, there's a like 100 step, okay, and then this kind of bottle drop from that step, and then it drops step by step, and then go down to from the top to the bottom, and this kind of bottle doesn't break. But instead of this bottle, I'm sure once you drop, it break, right? If you have a glass of this kind of glass bottle, it will drop immediately. It will break immediately. So this one is strong, light, can hold the pressure, and easy to deliver, and safe. You cannot fight, right? So is it wonderful? Yes, it is, right? So thanks for the innovation of the material. We found something good. Okay, and this is another material which is made of aluminum can. For this type of material, unfortunately, there's a kind of drawback. That is that if you don't use it for a period of time, for example, 3 years, the pressure will release gradually, very slowly. So you won't get the nice drink as you did 3 years ago. So the gas will release. However, if you have this kind of can, metal alumina, you can have a better taste for this kind of drink. Okay, so these are different type of material, but they all serve one thing, which is the sparkling drink, and they have different purposes. Okay, so some of you, I think you might be able to see this kind of bottle in the shop sometimes. Okay. For example, 1 month ago, I went to all you can eat buffet. You know, all you can eat buffet in Tainan, and they serve this kind of drink, a small bottle. You know, when you drink this, you can remember when you are young or something. Anyway, so these three type of the container all exist nowadays. They all serve in different purposes, but only for the sparkling drink. So this is glass bottle, and we call it ceramic. And this is metal. We call it aluminum can. And this is a plastic bottle, which is polymer. Okay, so we will introduce these three materials a little bit in this course. So let's move to the section 1.2, materials science and engineering. So what's the science and engineering? First of all, let's think of what's the science, what's the engineering. So you are engineer, right? Most of you. Okay, you might say, what's the difference between engineering and science? Anybody want to tell me? 0.5 points. Remember, you might get failed in the end of this semester, and you raise your hand now, I give you points. So you reduce the possibility of failing in this class. So raise your hand, you have nothing to lose. Okay, even though you got the wrong answer, I don't deduct the point from your final score. Okay, so anybody want to tell me what's the science, what's the engineering? If you are from material science, sorry, you are not from material science. I mean, what's the difference between science and engineering? Engineering make more money. Okay, yes, please. Thank you. Nice answer. Very nice. Okay, I think science is related to kind of fundamental. You know, they do it for most of them. For scientists, they do it for fun. You know, they do it. They found something interesting and they devote it into this kind of topic. They don't think of they might don't think of what is going to happen in the future for the application. How expensive is this? They don't think of this, but they are just curious about the things, and that's science. But for engineering, you need to think about, well, can I make money in the future? What's the application in the future? And can I make a mass production for this? Okay, so the way of thinking is different. When we train the students in the College of Engineering, or when we train the students in the College of the Science, the way of training is different. Okay, the material you learn, the things you learn is different. Okay, but anyway, this is the course of material science. So thank you for your answer. So so what's the material science? So the material science is the investigating the relationship that exists between the structures and the properties of the materials. I want you to remember this is that when you think of material, and you take a look of the material inside, and you find the different structures inside the material, and you need to think what kind of properties of this structure. So, and this is called material science. And how about material engineering? So material engineering is that on the basis of this structure, the properties correlated design or engineering the structures of a material to produce, that's important, is a predeterminate set of the properties. Okay, so if you are an engineer, you want to design a material, you need to think, what am I going to use this for? And when you know what you want to use this for, and you need to know how to construct the structures of this material. Okay, so it's kind of predetermined set of the property. Okay, So this is the material science and engineering. So, however, this is the course is material science, right? So let's take a look of the properties and the structure. So what's the structure? The structure of the material usually relates to the rearrangement of its internal components. What's internal components? There are 4 parts of this. The first part is called subatomic structure. The subatomic structure is that you have atomic. And inside atomic is called subatomic structure. Right? So electrons and the interactions with their nuclei. So you have atomic, and you have nuclei, and you have atomic. You have electrons. Okay, you want to see the relationship between the electron and the nuclei. This is one type of the structure. The second one is that the structure encompasses the organizations with the atomic and the molecules related to one another. So when you zone out of the atoms, you might have 2 atoms, 3 atoms, or 5 atoms together. And you want to know the relationship between these atoms. So this is called atomic structure. Okay? So what is the microscope structure? Microscope structure is that when you zone out again from the atomic view to hundreds or thousands of atoms, you will see another view of this structure material, and this is called microscope structure. So large groups of atoms that are normally agglomerated together observed by microscope. Okay, this is called microscopic structure. How about macro? Macroscopic structure is that the structural elements that might be viewed with the naked eye. So without using microscope, when you take a look of this material, and you can see, is this material shining, or is this material is spherical? So this, you can see the material. So this is called microscope structure. Right. So in terms of the science, material science, you need to relate to the material structure and the property. So what's the property? The property is, while in self-use, all the materials are exposed to external stimuli that evoke some type of response. So what does that mean? You have some of, you get, for example, if you have this material, and then there's an external force applied to this subject, and they will come up with some of the response. Okay? So there are some type of response. For example, if there's a polished metal surface, okay? For example, you have a piece of the copper, and you polish the surface very well, and the surface of the copper will reflect the light. For example, if the light hit the surface of the copper, and the light will reflect to you. This is what we call O type. This is O type of mirror, right? Okay, O type of mirror. Okay, so the definition of the properties that are made independent of the material shape and size. So when we talk about a property, we will regardless the shape and size. That's the independent. We want to think of this independently, not related to shape and size. So ladies and gentlemen, I want you to remember these 6 categories. Okay, it might be the Kahoot for next week. It might be in your midterm exam. So there are 6 properties. The first one, mechanical property. Mechanical property is a deformation of applied load or force. You don't need to remember the details, but I want you to remember these 6 items. The first one, mechanical properties. I'm sure you know this in your high school. There's no problem. The second one, electrical property. Okay, electrical conductivity, dielectrical constants, stimulus, electrical field. These are all related to the electrical properties. How about thermal property? The capacity, thermal conductivities, heat capacity, etc. These are all related to the thermal behavior. Okay, the fourth one, magnetic properties. The magnetic property is the response of the material to application of the magnetic field. So when you have a magnetic field applied to the material will have some response. And this is called magnetic properties. The fifth one, index of the reflection, reflectivity, electromagnetic of the light radiation. These are all optical property. The final one is called deteriorative characteristics. Well, you can regard this as a chemical property. Okay, chemical reactivity of the materials. So if you think of deteriorative characteristic, it might be too difficult for you to remember, and you can write down the chemical properties. Okay, so does anybody want to repeat this 6 for me? 0.5 point if you want to. In English or in Chinese, Mandarin. Isn't it wonderful? You got 0.5 in your final score. You just repeated 6 items. No? Yes, please. Yes. Okay. Okay, thank you very much. No problem, right? It's very easy. So let's discuss the properties one by one from now. Okay, the first one, mechanical stiffness. Okay, what's the stiffness? Stiffness is a resistance of an elastic body of the reflection or deformation of an applied force. Again, once you have external force or external things applied to this material, and this material will have some response. And in this case, you give force, and the response is stiffness. Okay, so the stiffness, the definition of this stiffness is reflection or deformation. Okay, so there are four types of the materials here. I want you to know that this is basic classification of the materials. There are 4 types. The first type is called metal. You know, metal, the aluminum can, right? Okay, the second one is ceramic. I just introduced you glass, a glass bottle. The third one is called polymer. You know, the plastic. Yeah, you know, the Coca-Cola, right? The polymer. How about the fourth one? Composite. Composite is a combination of the ceramic and polymer. It can be a combination of metal or polymer. So composite is kind of mixture of the materials. So I want you to remember there are 4 types of the classification of the materials. Okay, divided into 4 types. The first one is metal. Second one is ceramic. The third one is polymer. The fourth one is composite. Okay. So in y-axis is stiffness. You know, stiffness here, you from the low to strong. Oh, this is what? This is log, right? Log axis. Okay, so what is the strongest? Ceramic. The second one, which is a little bit lower, it depends on different material, right? For example, silicon carbide is the strongest. And glass is not that strong, but relatively strong compared to the polymer and composite, right? Okay, how about metal? Metal is very strong. Toughness, tungsten is the strongest. Steel second. Okay, the weaker is magnesium, aluminum. Okay, but it's still relatively strong compared to the polymer. These are all different type of polymer. Okay, P stands for poly. PVC, PS, polystyrene, PTFE, PE, rubbers. You don't need to remember this very well, but I want you to know this bakery because you know the ceramic is the strongest. Second, metal. Third is composite because you combine the ceramic and polymer together, right? So you will have this. Okay, the polymer is the last, very weak. Okay, so what is CFRC? CFRC, carbon fiber reinforced composite. Okay, GFRC is, you know, you check Google, you can find out this, the glass fiber reinforced composite. Okay, so this log scale tell you that you don't do this, you know, if you want to compare this 100 to 0.1 is large scales. So what you want to make is you want to make it as a log scale so you can see easier for the comparison. Okay, so the stiffness, the next one is strength. So the definition of strength, here we introduce tensile strength. Tensile strength is the strength that at which the materials break or permanently deformed. You know, the previous page tells us the deformation, but it's not permanently deformed. You can recover, but this one strength we talk about the permanently deformed. Okay, again we compare 4 types of materials. So metal, ceramic, another way around. Okay, and then polymer and composite. Good. Another one is resistance to the fracture. Okay, fracture is broken. Deform doesn't mean break, right? Deform means you cannot come back to the original shape. But break means that you break it, you permanently break, and you cannot put these two together. So this again, this is kind of comparison. So as you can see, the ceramic drop, you know, the scale drop. Why? You know, when you break, when you give a force to this ceramic, it break. For example, if you have ceramic bowl for your rice, you eat rice, right? Okay, except some of you from overseas. So if you have a ceramic bowl and you break it, that'll be easier. But can you break metal easily? No, metal cannot be break easily, right? So as you can see from here. Okay, the next one is electrical conductivity. So the second type of the property is called electrical conductivity. So this is the metal. Of course, you know metal has a very good conductivity, electrical conductivity. Okay, and you know this one changed from the composite to the ceramic, to a semiconductor, because you know the ceramic and polymer get together, they don't have conductivity at all. So we use another category to replace the composite, which is semiconductor. And this is a very strong industry in Taiwan, right? Very high pay, okay? But you need to spend a lot of time in the company, okay? Even at night when you sleep, when you get a phone call, you need to get up and then go to the company to work. Or if there's a kind of trouble you need to solve. I'm sure most of you, or I will say 2 out of 3 of you will go to this kind of industry in the future. Okay, so electrical conductivity, the first one is metal, which is a very good conductor. And then between the insulator, which are ceramics and polymer, between this is a semiconductor. As I told you, this is a very popular study in Taiwan now. Okay, this is one of the examples of the electrical resistance of the copper. So the x-axis is the temperature. Y-axis is the resistivity. Okay, it's the reciprocal of the conductivity, right? If you have a good conductivity, then you will have a very poor resistivity. Okay, so let's take a look of the pure copper. Okay, when you increase the temperature, and then what? The resistivity increase. Okay, when you reduce the conductivity, when you reduce the temperature, the conductivity increase. This is common sense, right? It makes sense to you, right? Okay, so importantly is that when you add 1.12, what is this? Atomic percentage. So if you have one atom here in copper, you have, sorry, if you have 100 atoms in this material, then you have, sorry, you have 1.12 atoms in the nickels in these materials. Well, I should say 98.88, right, percent atoms in the material. Then you have 1.12 atoms in the nickels in this material. So this is what we call, this is called what we call impurity. So you know the copper is a very good conductor, but if you put impurity into this copper, what kind of the good property will change, right? To bad, to worse. So as you know that when you add impurity into this copper, the resistivity increase. It makes sense to you, right? Okay. And when you increase the temperature again, the resistivity increase. This is what we are going to talk about this in chapter 4, which is what we call impurity, or we call defects, or we call imperfection. Okay, this is called impurity. Okay, another impurity is we call dopant, which is good, but I think it's too far to introduce this topic to you. I will talk about this in details in chapter 4. Okay, let's take a look of the next line here. This is called deformed copper with 1.12 atoms nickel. What? Oh, okay, forget about this first. Once you increase the percentage of nickel, what happened? The resistivity increase. There's no doubt. Right? No doubt. Okay? And if you take a look of this line and this line, the differences is this is a good copper. I don't want to say good copper, but at this moment I just tell you this is a copper which is the structure is very perfect. It's a perfectly copper. But this is called deformed copper. Deformed is that kind of, if you have an atomic rearrangement which is not perfect, okay, it's not crystal, or we call polycrystal amorphous. I don't know you know this term or not, but anyway, this is imperfection. This is not perfect copper. This is perfect copper. If we put not perfect copper with impurity together, of course, you understand the resistance will increase too. Okay? So I hope you understand this figure. So temperature increase, resistivity increase. And adding impurity atoms to the copper increase the resistivity. Okay? And deformed copper decrease the resistivity. Okay, let's take a look at the thermal. Right, this is the space shuttle tile. You know, this is space shuttle, right? Recent news, there is no recent news about the space shuttle, but anyway, this space shuttle, you know, when space shuttle goes through these atmospheres in the Earth, you know, because of the high speed, and they will have interaction with the airs, the molecules in the air, in the space, and the space shuttle will produce a lot of heat. But you don't want the people inside the space shuttle get burned, right? So outside is very hot, but you need to keep the inside very cool, right? Room temperature. That's why the people inside the box will be safe. And so you need to have a material which can resist very, very high temperature. How high? It's about 20 2200 Fahrenheit. And you know, inside this, the temperature inside is 2200 Fahrenheit, but you still can hold this brick with your hand. What does that mean? The outside temperature is room temperature, or like 60 Celsius. So you can hold this, but inside is very hot. So when you take a list, another way wrong is that outside is very hot, but inside is okay. It's at room temperature. Okay, so this is a very important materials. So when we use microscope to take a look at the structure, it looks like this. It's fibers, a lot of fibers made of silicon dioxide, and low density. So the type of the low density surface insulate the composed almost entirely the silicon glass fiber. What does that mean, silicon glass fiber? This is silicon glass fiber. This is made of SiO2. And this is in nanoscale, very, very fine powders. Very, very fine fibers. And they put it together to become like this. And the porosity is about 94. So there are only 6% fibers in this brick. Okay, only 6%. So another 94% is empty. There's nothing. So that's why this is a very good thermal insulator, sorry. Okay, let's take a look of the a video I want to show you. You really cannot see. It's very, very hard, but you will be hesitate to touch it. But when you touch it, it doesn't happen. It happen nothing. Okay. So I can make this in my lab. There's no problem. It's silicon dioxide. But you can make this in the lab. That's what? That's science. Okay. If you want to make this everything that's exactly the same, and you can put this in the shuttle space, that's engineering. Okay. You make this mass production, and everything, all the bricks looks the same and perform the same. Okay. Right. So this is another property we call thermal conductivity. You know, the previous two slides we introduced electrical conductivity. How about thermal conductivity? Okay. The thermal conductivity is that you have composition. You have copper again. Copper also is a good conductor, and then you put the zinc into the copper. So with the increasing the percentage of zinc in the copper, the thermal conductivity decrease. Okay. How about if you increase to 40, you will be here, right? So if you can write a mathematical equation for you to calculate this, so you can do the prediction. Okay, this is another interesting thing about the science and the engineering. Okay, if you can write down an equation to represent this curve, so you can do the prediction. You don't need to do the experiment. Okay. Recently, there's a very nice movie. It's called Oppenheimer, right? So he can use pen and pencil to calculate how strong the nuclear bomb damage. Just use his brain and piece of paper and pen and do the calculation. That's called prediction. Okay, the third one is called magnetic properties. I'm sure you know this is in your hard disk, in your computer, you always use this for the memory. It's called magnetic storage. You know, we live in this digital world. Everything is run by 0 and 1. Okay, so you store 0 and 1 in one type of storage. And there's one type of storage is called magnetic storage. And when you have your USB, that's electrical storage, right? Okay, we call flash. That's a different story. Anyway, so this is you know, you can change the domain from the right to the left, and you can define this as a 1 or 0. Okay, so this is the magnetic properties. So important is, can you find this kind of materials and change the domain? Okay, you find a good one and you change the domain. Again, this is the electrical field against the magnetization. Okay, and this is silicon impurity, and if you put the silicon in, seems the magnetization is increased, which is good. Okay, so this silicon can regard as an impurity, but there are some impurities good for the material structure, for the property of the material. There are some type of impurity which is bad for the property of the materials. For example, if you have a if you have a portion of the porridge, for example, and you put the salt into the porridge, it tastes good, and the salt will be the impurity, which is good in this case is silicon, right? It tastes good for your porridge. But if you put some of the dust, or you put some of the spicy things, and it tastes bad, right? So that's bad impurity. Impurity. Right. This is optical differences between the three objects here. I want to tell you is one. These three are all made of aluminum oxide. Exactly the same. Inside is only aluminum and oxygen only. However, because the structure is different inside this, there's no copper, there's no nickels inside these materials, but only alumina and oxygen. And because they put it together in different manner, and you can see this one is transparent. This one is not. It's about it's not very transparent. It's half transparent. As you can see, the letters, English letters behind this object, right? Substance. And this is absolutely opaque. So you see nothing. Okay? And they are all made of alumina oxide. And this is what we call single crystal. It's different structure. The same atoms, materials, but different structure. This is what we call single crystal. So it's highly perfectly. That means the arrangement of the atom or arrangement of the alumina and oxygen are very ordered in the materials. This is what we call single crystal. It's transparent. And this is the polycrystalline. So there are a lot of small single crystals together. Not everything is perfect, but you have small parts. You have many polycrystalline get together. So numerous small single crystals are connected. And this is polycrystalline. I think we will introduce this in chapter 3, okay, in this lecture, in this course. And this is the polycrystalline with 5% porosity. Porosity means that there are 5% empty space in this material, only 5%, and it's opaque. You see nothing through this object. Okay. You also have one component in your body. This in your eyes. This is called lens. Okay. When this lens is like this, you see everything is wonderful. Okay, it's very clear. Okay, if this is made of protein and it's crystalline protein. Okay, and when you have some damage with this lens, you see blue. You cannot see very well. Okay. Of course, if you doesn't care about your eyes, and then the crystalline get worse, then you have to replace this. In Chinese, we call 白内障. Okay, I already changed this to artificial lens. So if you want to use your smartphone every day, 24 hours, sooner or later you need to change this. Okay, because the light will go into your body, and then this lens is crystalline protein will change its formation from single crystal to become polycrystal, and you will see not easily, gradually, and then you need to change this lens. Okay, like me. Okay, the final is that deteriorative properties. Okay, so you will see that when you put these things in the salt water, the salt water will damage the metals, and you crack, and it will have kind of corrosion happen. So this is kind of chemical properties. So I basically introduce you the structure and the properties. You know, there are 4 types of materials, and there are 4 scopes of the, there are 4 levels of the structure. Okay, there are 6 categories of the properties. Okay, so you can see that the 4 components of this discipline of the material science and engineering is that you processing the material and you see the structure. And when you see the structure, you want to test the performance, or you want to test the property. And if property good, you take it out to do the application, to do its to see its performance. Okay, so this is the way of the doing the linear relationship between this processing, structure, properties, and the performance. Right. I'm happy everybody wake up, and let's continue the course, the lecture. Okay, the section 1.3, why study material science and engineering? Well, because, you know, I just skipped this section because you are here and you are interested in material science and engineering, right? Okay, so next, the section 1.4 is a classification of the material. First, okay, I want to tell you that there are many types of materials, and in this course, we only talk about solid material. Okay, among the solid material, there are 4 categories. The first one is metals, second one, ceramics, third one, polymers, and fourth one, composites. Okay, I'm sure this, you know that metals, the metallic materials are normally combination of the metallic elements. If you put 2 elements together, it becomes alloy, right? If you have one element, it's kind of pure metal. So large numbers of the non-localized electrons, which are not bound by particular atoms. That's why this metal has a good electrical conductivity. Okay, the properties of the metal, I'm sure you all know from your high school. So the good conductors of the electricity, the good conductors of the heat, we call heat conductivity, right? And electrical conductivity. And it's not transparent to visible light. Why? Why all the metals is not transparent for the visible light? We'll talk about band gap in the chapter 2. Okay, that's why you know why it's not transparent. The fourth one is strong. It's very strong. So you can see these metals. How about ceramics? Ceramics is that ceramics are compounds between metallic and the non-metallic elements. So if you pick up one element from metal groups in your periodical table, and you pick up one element from the which is belong the non-metallic group in the periodical table. You put these 2 together, this is called ceramic. Of course, this has to be in the form of solid. Okay, this has to be in the form of solid. That's why we call ceramic. Right. So the property of ceramic is that insulative and the passage of the electrical and the heat. So the ceramic cannot conduct electrical, and is a good insulator, electrical insulator, and also also is a good insulator for the heat. Okay, so when you eat hot pot 火锅, okay, if you eat hot pot in a very high class restaurants, it always made of the container for hot pot is always ceramic. Why? Because it can keep the heat very well. It's not stainless container. But if you go to cheap hot spots shop, you always with that, right? Always with that. Anyway, so the hot pot, the ceramic can keep the heat, so you can enjoy the food for a long time without heating the soup, right? Without heating the hot pot. Right. So the ceramic can be a clay, minerals, cement, and glass, and so on. Okay, these materials all belong to the category of ceramics. The third type is called polymer. Polymer is actually organic compounds that are chemically based on the carbon, hydrogen, and other non-metallic elements. Right? So it's kind of polymer means large amount. Okay. In contrast, we call monomer is small molecular. Monomer means small molecular. If you put monomer together, it will become a large molecular structure. To make it become a large molecular structure, it will become polymer. And then because it doesn't pack very well, so the density is low. Okay, and maybe extremely flexibility. Okay, you can bend the polymer, you can bend the plastic rubbers, right? So the plastic rubbers material belong to the type of the polymer. Okay, you have helmet, right? You can have bottle, you can have tire, the plastic knife, forks, spoons. This is polymer. Right. For the composite, you have tennis racket, right? Tennis racket you play very nicely. When I was young, we use aluminum racket frame, okay? Or even in a much older time, they use wood to play tennis as a frame of the tennis racket. And now you use composite, carbon fiber composite, right? And this mainly is made of carbon fiber composite. So composite is designed to display a combination of the best characteristics of each of the component materials. So composite, glass fiber, if you put a glass fiber mixed with polymer, we call this glass fiber composite. So glass fiber embedded within a polymetric material. And if you replace glass fiber to become carbon fiber, we call this carbon fiber composite. Okay, so you have fiber, this is glass fiber. You have fiber and you put resin or you put polymer, you apply polymer soft between these fibers, it becomes like this. This is the carbon fiber, and this is glass fiber. And in the end, you make a product, like a very strong light cover for your smartphone. Right. So in order to reduce the cost of the fuel in the airplane, you need to make the airplane very light. And this is a new design of the airplane commercially. It's Boeing 787. There are some parts, mainly in the old times, always metal for all the planes. And now you use glass fiber, you use carbon fiber to replace the materials. So it makes it light. As you can see, the composite in the in the composite content or composite in this airplane is high. Okay, for the 787, the composite is about 50%. For 777, the composite, the alumina is about 50%. It's about half. Okay, so next, advanced materials, section 1.5. So what is the definition of the advanced materials? Advanced materials that are utilized in a high-tech, or we call high technology or high-tech applications, are sometimes termed advanced materials. What does it mean, high-tech? High technology, a device or products that operates or functions using relatively intricate or sophisticated principles. So, if you use this material or you use this device with the principle of quantum mechanics, you can regard it as high tech, right? But if you use this according to Newton's principle, well, sometimes, I'm not sure you can call this high tech or not. So advanced materials, the materials are used for laser, integrated circuits, magnetic information storage, liquid crystal plate, or fiber opticals. They are all advanced materials, belong to advanced materials. Right. So in my class, if I say, well, this is important, this will be in your final score, or this will in your midterm exam, and please remember, if I don't say that, or you don't need to remember this kind of, I don't want you to remember this kind of words. You just know the basic, what does that mean? You don't need to copy everything out, okay, in your final exam or in your midterm exam. I just want you to know important things and put this in your mind, and you can use this knowledge for your future. Right. So advanced materials, semiconductor is very important. You know that. And biomaterials is also advanced material, and material for the future. That's what these three topics we are going to introduce you now. Materials of the future, smart materials, or nano engineer materials. Wow, the first one, semiconductor. Semiconductor, the electrical properties are intermediate between the electrical conductor and the insulator. The why semiconductor is important is the conductivity of the semiconductor is between conductor and insulator. So if you can tune the conductivity using this semiconductor, not temperature, but by change the structure of this material, you can tune the conductivity. That's why it's important. Okay, using this property, have this material, then these materials are extremely sensitive to the presence of the minimum concentration of the impurity atoms. So if you have a silicon, we know silicon is a type of semiconductor. If you put boron into this silicon, or you put the phosphate into this phosphor into this semiconductor, you can change the conductivity. And that's important. So once you change the conductivity, you can design this kind of material to become a device. For example, like a diode, like transistors, like capacitor, like resistor. Okay, so if you just change, mainly it's transistor and diode. So if you can tune, you can design the property of the semiconductor, you can make it become a device. Okay. So semiconductor is electronics and computer industries. Now AI is very popular. Without semiconductor, you cannot run AI. Okay, you cannot do anything with AI. When I was young, 20 years ago, no, 30 years ago. Okay, and I actually I started to study AI, okay, 30 years ago. But unfortunately, a lot of times the speed of the computer is not that fast. So when I was young, I was in my university, and I went to library because library has 100 computers. So I use 20 computers to run my program in the middle of night because nobody stay in a library for study, and I'm the one, a Chinese, go to the library to run 20 computers and then run the AI program. Okay, but now you don't need to. You just use your personal computer and then you just play. You just write your program. You just write code and you can run AI. So now, thanks to the semiconductor, they make the technology go through very fast, and you can enjoy the life of AI. Right? But for this kind of industry, is very, the semiconductor industry in Taiwan is very important. And if this kind of industry disappear, Taiwan will disappear, Okay, so it's important for the engineering to go to this industry and then work on this industry. And why is it important? Because, we call this is called wafer. This is called wafer. And inside this wafer, you will have chips. Okay, these small pieces called chips. And chips is very small. And inside these very small chips, you will have billion transistors. Not billion, it's a billion scale transistors. Okay, very small. If you think of 1 centimeter times 1 centimeter, you might have 1 billion, maybe 10 billion transistor inside. It's not easy. This is not the problem of the science. This is the problem of engineering. Okay, if you have one transistor inside, is 1 centimeter times 1 centimeter chips. That's easy. 10 easy. 100 transistor easy. But 1 billion and 10 billion transistor inside this chips, not easy. Okay, so that's why we need engineers to work on this. Okay, the second topic is called biomaterials. Biomaterials is that the components implant into the human body for the placement of the diseased or damaged body parts. For example, if a jaw here and you place this soft tissue to become a metal, to become a human-made materials, this is called biomaterials. So it doesn't matter it's metal or it doesn't matter it's polymer or composites. If you put this into your body, this is called biomaterials. Why? Because your body is very important. It's important. It's not a toxic substance, and it has to be compatible with the body tissues. Otherwise, you have trouble with these materials. You cannot put the materials into this body. Anything you can put this into this body is called biomaterials. And you need to match these two criteria. Okay, so it can be metal, it can be ceramic, it can be polymers, it can be composites, it can be semiconductor. Okay, if you implant a chip into the body of a cat's body or dog's body, this is a biomaterial. As long as it's not toxic, as long as it's compatible with the body tissues. Okay. How about smart material? Okay, smart material is important because we need smart materials to make smart devices. Okay, so what is smart material? Smart material is that the materials are able to sense, can feel the change. So if I'm a material, I can feel the change. Okay, not only feel the change, but I can respond. For example, if you have sound coming to me, I can talk to you something. So our sound is changed, and then response is voice. Okay, so the components for the smart materials include two parts. Okay, I want you to remember this because sensor is sense the change. You sense the change. And response we call actuator. Actuator, response. Perform a responsive and adaptive function. So there are two components in the smart materials. The first one, sensor. Second one, actuator. I want you to remember this. Once you start to design a smart materials, these two are important. These two are the necessary components you need to remember. Otherwise, you cannot make a smart material. I'm going to give you an example very soon, but let's define the actuator. You know, sensor is easy, right? So what is actuator? Actuator might be called up on the change. You can change the shape, you can change the position, you can change the frequency, you can change the mechanical characteristics. Once you suffer the temperature change, electrical field or magnetic field, so it kind of responds. Okay, so here we are going to introduce you 4 types of actuator. The first one is shape memory alloy. Second one, piezoelectrical ceramic. Third one, magnetoresistive materials. The fourth one is electro-rheological fluids or magnetico-rheological fluids. I think we run out of our time today. Next week, I will start our course from this page, and we will start to introduce you what's the shape memory alloy, piezo, electrical ceramics, etc. Okay, right. Listen to the lecture. I hope you enjoy the lecture. And finally, want to do the